Folks, can you hear me? Oh, yeah, I guess you can.
Rito, I think they're doing parties over there.
What?
They're doing parties over there.
They are doing parties over there. We'll have 210 party. So we will get done with SN2, SN1 E1 and E2, and if we have some time, we'll look at the residual stuff from yesterday. All right? So first of all, our favorite reaction, the SN2. Everyone hears me, right? Over the party noise from the next door. All right, so SN2 reactions. Now, what does SN2 stand for? Substitution. And N is nucleophilic. Second order. That means this is a substitution using a nucleophile. And why it's second order? Because this reaction in its slowest step involves two species. By the way, this reaction has only one step, right? So therefore that is the slowest step, where the nucleophile goes and attacks the electrophile, which is the backside of the C leaving group bond, makes the leaving group leave, and you have this product which forms through a what kind of inversion? Walden inversion, all right? Backside attack, giving a single isomer of the product through a Walden inversion. Now let's look at these things individually. Now when I say backside attack, backside of what? Would I be right if I say backside of the carbon? No, the carbon doesn't have a backside. It's like if you look at the model set, the carbon is a spherical ball, right? So backside would be of the carbon leaving group bond. Why does it attack from the backside? What orbital is it attacking on? All right, you're trying to break this bond, right? That is what bond? Sigma. To break a sigma bond, say this is a if I start dancing, don't blame me. It's the music. So, if the nucleophile puts its electrons over here, what's the bond order right now? Bond order means number of bonds, which is also equal to number of sigma electron minus number of sigma star electron divided by 2, and that is number of bonds. Which you know, between the carbon and the leaving group, there is one bond, right? The other way of finding out number of bonds is by doing this math. Number of bonds in the sigma, which is 2, minus number of bonds in the sigma star, which is 0, divided by 2 is 1. And that's the same answer as that. To break the bond basically means making the bond order 0, right? Bond order is the number of bonds. If you break the bond order goes to 0. How can you make the bond order 0? By putting 2 electrons over here. All right? So where are you putting the electrons? On the sigma star. Do you get it so far? You can ask me questions. Yes, sure. So I'm trying to break the carbon leaving group bond. How do we break the bond? Before we go to that, we have to understand what is a bond from the electronic perspective, all right? In the electronic perspective, the number of bonds can be found by doing this math. Number of sigma electrons minus number of sigma star electrons divided by 2, which in this case is 1, and you know there is one bond between carbon and leaving group. To break the bond equals making this bond order go to 0, all right? How do you do that? If you put 2 electrons over here, that means now the bond order equals 2 minus 2 divided by 2 equals 0. That's why if you have the nucleophile put electrons in the sigma star, the carbon leaving group bond will break. So your nucleophile is putting electrons, and this was a question in one of your homeworks. That's a sigma star. Okay? So nucleophile puts the electron in the sigma star. Question over here at this point, if you can hear me. Now, second thing is, do you get this part? All right. Second thing is the Walden inversion. Now you can see, since the attack happens from the back side, all right, not from the side, nucleophile comes in from the back and not from the front, not from anywhere else. That's why your product is unique. You only get one product where you have a Walden inversion. Let's see what I mean by Walden inversion. Let's take up this example, this first example, all right? In that question, can I erase this? So we're trying to understand the Walden inversion. So, what's the leaving group in this material, starting material? Iodine. So once it leaves, it's a backside attack. How would your product look like? Do you think that's right? Comes in from the back, pushes these forward. Let's comes in from the back, pushes these group forward, right? It's like an umbrella flip. This nucleophile comes from the back, these groups move forward. These groups have moved forward. That's what I did. Came in from the back, so these move forward, and the nucleophile is now sticking out from the back, right? So that's my inversion. Now let's find out R and S on this carbon. So what's the highest priority? Iodine. Second is? Third is? All right. So if I do 1, 2, and 3, oops. 1, 2, and 3 is? Counterclockwise, right? Lowest priority is the back. Let's look at that. Who is the highest priority here? Second is? There are 2 carbons, right? So you stand on this carbon. What's on this carbon? What's on that carbon? Hydrogen. So which gets higher priority? So this is number 2, that's number 3. 1, 2, and 3 once more is? S. So you had an inversion, but S remained S, all right? So this inversion is not related to this absolute configuration that you assign on these carbons. That's why it's called a Walden inversion. All right? It might be R, might be S. That depends on what's the nucleophile and what the other substituents are. You know there's inversion, but S might not go to R. That's why it's not called just an inversion. It's called a Walden inversion. Do you get it so far? All right. Now, SN2 is going to be our favorite reaction. All right? Our approach is going to be whenever you see a reaction, we'll start thinking of it as an SN2 reaction. And then we'll look for hints of what detracts us from an SN2 reaction. All right? So SN2 is our favorite reaction. Why is it favorite? Because bond breaking, you know, the BDEs that we have are positive numbers. That means you need energy to break a bond. When you're doing an SN2 reaction, the bond breaking is compensated by the bond formation. They happen in the same step, right? It's a concerted mechanism. Therefore, SN2 is favored over first order processes. What happens in first order processes? I'll just skip forward just so you can see what happens in the first order process. You see in the first order process, the leaving group leaves first. You get a carbocation. There's nothing to compensate this first step, which is the slowest step. So first order processes are not as favored. We'll see it, we'll come back, all right? Just keep in mind SN2 and E2 are more favored than first order processes. Now, if the nucleophile has to come in, you would need a hindered substrate or a less hindered substrate? less hindered substrate. We'll do problems on each one of these properties, so don't worry if you can't remember them right away. So less hindered substrate, the best substrate is a CH3, all right? So that means if I have a CH3I, that will give me the fastest SN2 over an ethyl iodide, all right? That's a CH3. What is this first order, primary, secondary, tertiary? Primary. How do you find out primary? By the number of carbons it's attached with, nothing else, all right? This is secondary, right? So this is better than that better than that in terms of SN2. The worst is tertiary. Tertiary almost doesn't give you an SN2 reaction, all right? Now let's look at the problems. What is the first problem? Let's do the second one. What do you think that is? That's my nucleophile, right? Might look scary right now, but as we go through it, we'll list what nucleophiles are, right? And you'll not be afraid of this anymore. Sulfur with a minus, that's a nucleophile. So this nucleophile is going to attack this substrate, right? Which is a leaving group on the substrate? The iodine, good. How would you draw the product? How would that look like? Now we say it goes via a Walden inversion, right? Would I do an inversion on that center? No, I would not, because I am not doing a substitution on that center. I will not do a Walden inversion on that center, all right? That's very important, because some of us, when we study, we think SN2 implies we get an enantiomer. No. All right? Inversion happens only on the carbon that has a leaving group, not on all the chiral carbons. This one has a leaving group. That is the one that's going to undergo an inversion. So I'll keep this carbon the way it is. This huge group that we are scared of right now, how should that point? Outwards or inwards? Inwards, right? It's a Walden inversion. S, pH. Makes it look less scary, right? pH is better, right? Now, get this problem? All right. Next feature of SN2 was backside attack. That's what we're going to exploit on this problem. Say you have and what is the purpose of NaH? Is hydride my nucleophile? No, it's my base, all right? We use that when we're doing ethers. It's my base. What does that do? The H minus picks up the proton. Don't say hydrogen, proton, proton. That. To have a suitable SN2 reaction, where is the leaving group? What's my leaving group? The oxygen is my nucleophile. The iodide is my leaving group. Now, would you have this oxygen attack this carbon, or would you have this oxygen attack one more of the starting material? That is, would you rather do an intermolecular or intramolecular? Would you have this attack on the carbon, or would you have this attack here? Intramolecular is better, all right? Because I can punch myself faster than I can punch someone else. Having a tethered nucleophile is always better, all right? So intramolecular is always favored, and we will see that. So now, is this oxygen aligned in the right fashion? Is it facing the backside of the carbon? By the way, that's wrong. What should I say? Backside of the carbon leaving group bond, all right? What is the backside of the carbon leaving group bond? Trace this line backwards. That's where the backside of the carbon leaving group bond is. Is the oxygen facing it? You turn it, right? So I'm going to turn it around this sigma bond. I'll keep the oxygen upwards. If I turn it, the I will point downwards. Now you can see this kind of conformation is called anti-periplanar. Periplanar means on the same plane. Anti is when they're pointing in opposite direction. Now, how would my methyl point now? Out of the board, inside the board. 180, right? I'm taking this and I am breaking this down. This was pointing out, it will go in and up, right? Can you visualize it?
Yes.
Right? Do you envy the happy people next door? That's a loud music. So that. Now, you have a Walden inversion. Walden inversion means what happens in a Walden inversion. Let's look back once again. You get an umbrella flip, right? These are pointing like that. They will move forward. So this was pointing up like that. Do you need to do anything fancy? What do? You just point this downward. That's it. You don't bring it in or out. So how would I put this methyl? Dashed up or down? Down. On this carbon? Do I invert on this carbon? Everyone gets why? Because I'm not doing a nucleophilic attack on that carbon. That is my product. Okay? Now, the next one. Get it so far? All right. So I'll give it a raise. Let's try this problem. N3 minus, by the way, so we are going to deal with a lot of different kinds of nucleophiles, right? Now these nucleophiles will seem new, but as we go through it, we'll list all the nucleophiles. This will be every day after a while. Now, so I'm going to do a nucleophilic attack. Which of these carbons would undergo the nucleophilic attack? The one bearing the leaving group, which is? Methyl? No, I'm sorry. The iodine, right? Yes. This H minus, you're saying it will attack? It does not. Whenever you have a strong base, you will pick up an acidic proton first. All right? That gets picked up first before you do a nucleophilic attack. If I used a Grignard reagent like CH3MgBr, I will pick up the H first. All right? So, yeah.
I had a question.
Yeah, sure.
Since it's a ring, wouldn't that hinder from attacking the backside? Up there, the other one.
Oh, and that one?
Yeah.
No, it will not. It's so that's the cyclohexane, right? No matter how I put it, this or like this, how would you say it's hindered? It always has an exposed backside, right? And that was not me. So you undergo a SN2 reaction on that center. And if I had to draw the product, it will undergo a Walden inversion. How would this N3 point? Outwards or inwards? Inwards. Everyone gets an inwards and there's the answer? Okay? So that's clear with us, right? Okay. Yeah. Why is it inwards? Because it's a Walden inversion, right? Basically, it comes from the backside. The backside of this will be an inwards, right? What if I showed the H like that? Would that confuse you more? How would the H point over here? Outwards. You know the trick of doing this problem if you are kind of confused? Replace the leaving group with a nucleophile and then switch two groups. So I would do it like this. I would think of it like this. This is a thinking process, right? It's not the answer over here. I would switch the leaving group and the nucleophile. Let's switch two groups on this carbon and then replace the leaving group with the nucleophile. That will give you the right answer. In case you are having a problem visualizing, I don't want you to make models in the exam. That will take a lot of time. Switch two groups on that carbon, replace the leaving group with the nucleophile. We'll give you the right answer. Okay? Now, next problem. These substrates and how do they respond to an SN2 reaction? So which of these substrates, so what should we look at? This is my order, right? As you can see, these substrates only vary by the substitution on the carbon bearing the leaving group. So what's best? Methyl's the best. We don't have a methyl over here, do we? No. So A, B, C, D, which of these have a primary carbon? B and A. So I'll list B and A first. Friday happens to be a happy day for some reason. Until you go to grad school. All right? So these two are my most reactive. What comes next? Now you got C and you got D. Which will you put next? Anyone with C? That carbon, whenever you're doing a substitution reaction, do not do a substitution reaction on anything other than a sp3. We will do a substitution on an sp2 later on, all right? Using what? Cuprates. Good. Nothing else so far. Unless you're doing a nucleophilic aromatic. No, that's right. I mean, don't forget that. So substitution on a sp2 carbon with cuprates. All right? And unless you're doing a nucleophilic aromatic. How about this carbon? Secondary. All right? So C is the worst. I'll put C at the last. This. Now, between A and B, what would you, oh, is it B? Yes, B. Which one is better? Whenever you have a p orbital next to the carbon bearing the leaving group, that is always better, all right? We'll look at these factors once again. We're just warming up at this point. Why is this better? Let me draw it out. A will look like this. A will have the leaving group leave. That. You see how this p orbital that forms here, that's that carbon. This is your double bond. How the p orbital is stabilized by interaction with this pi bond. See it? So having a pi bond adjacent to the carbon bearing the leaving group is always good. That's good for second order reaction. That's also good for first order. We'll wait till we get to the first order reactions. So what's the order? What's the best? A is the best. Next is B. Next is C or D? D. Last is C, right? All right. A similar question, just to figure out how well we understood what just happened. The last one. N3 minus is also nucleophile. I just varied the nucleophile, right? Because changes, good. Change the nucleophile. Now, which substrate is the best? In the last problem. So we'll first look at, see, this is a, what kind of substrate? Tertiary, all right? I would not pick that. So let's see if I have a primary. Which are primary? Is this primary? Yes. Yes, so D is primary, I'll put D. What else is primary? B is primary. So these are better. We'll rank these later. Which is that's better than C, because that's not tertiary, right? And these are better than A, which kind of never will give you an SN2 reaction. That. Now, between B and D, which is better? D. Why? Exactly. So D is better than B. Everyone gets it? No question? So we are moving on. The next reaction is E2, which is once again a second order reaction. Why is it second order reaction? Because how many steps is it? Single step. And in that single step, you need both the substrate and the base taking part to give you the product. All right? That's why it's a elimination second order. That's what E2 stands for. So base pulls off the proton, which kicks out the leaving group. This is a transition state. Why is this a transition state? Why is it not an intermediate? Because I don't know how long these bonds are. I don't know which bond is formed by how much, which bond has broken by how much. I don't even know what these delta values really are. Is it half? Is it 0.3? All right? I'm unsure. Whenever I'm unsure, I put my confusion in a bracket and put a double dagger and call it a transition state. So that's a transition state. Gives you the product. As you can see, once again, the product is a single product, right? So both for SN2, which you get a single product, and E2, you get a single product, single enantiomer of the product, right? Or single isomer of the product. So first is this arrangement, which is anti-periplanar, the leaving group, and the base, BHC, this bond, and this has to be at 180 degrees on the same plane, all right? Now, is the bond breaking compensated by bond forming? Yes, it is. You're breaking this bond, and you're compensating that by the formation of this pi bond as well as the formation of the BH bond. All right? So it's much better than the first order reaction, where the bond breaks first. Get it so far, what you just said? Please ask questions if you have them. Now, you have a question? No. Okay. Something else we'll see is Zaitsev elimination. What does that mean? We'll see. Which basically means you would form the more substituted alkene. For example, this is the leaving group, right? And you're picking up a proton from the next carbon. Now the leaving group's next carbon is also that. The leaving group's next carbon is also that. Do these carbons have hydrogens? This one does. This one does? Yes. This one also does, right? So why am I picking up the proton from this carbon and not from these carbons? What's the universal rule? The poor gets poorer, right? So you pick up the proton from the carbon that has the least amount of proton. Right? That's what the Zaitsev rule is. So if you have more than one carbon, just because I drew the substrate like that, all right, it makes it easier for you to spot. We'll have problem like this one, where you don't know which proton it is, right? Because I did not draw a substrate that lets you get biased. We'll look at those problems. So you would form an alkene by pulling off a proton from that carbon which has the least number of proton. Otherwise, you form the more substituted alkene. Get it? That's a Zaitsev elimination. And you get a single isomer of the product. Let's do some problems. So we'll do problems on E2, and then we'll see how we can find out when E2 works, when SN2 works, all right? So the first problem. You got these two substrates, and you're trying to do an E2 on it, all right? This is a base. We'll see what's a base, what's a nucleophile. Just for now, take it for granted that this is a base, and bases would give rise to an E2, not an SN2, right? We're not going to do an SN2, we're going to do an E2 elimination. So these two substrates, which will give you an E2 better, faster? Let's see. The right one's always right, not the wrong one. Right? Now, how would you put the isopropyl? Now, that's the group that will decide how this thing ends up. Say you want this, and you want both of them to go to the. Right. Let's see. How would you put the isopropyl? Equatorial or axial? Is it pointing up? Is it pointing down? Pointing up. So if the Br is cis, would it point up or down? Right? Do you get these two as cis? How do you decide cis or trans? Cis or trans is not decided by being axial or equatorial. It's decided by which way you're pointing, up or down. This is pointing up, that's pointing up, there's cis. Okay? I draw this now. Once again, in this substrate, the isopropyl points up. This kind of representation doesn't mean the isopropyl is pointing down. It means these two are trans. That's all it means, all right? Don't take it as this meaning the isopropyl is pointing down. If that's pointing up, the Br is pointing. And always draw the protons. That helps you. Okay, now, okay. I have to do an elimination, right? An elimination needs my leaving group to be what? With the anti-periplanar, good. So I draw the protons over here. And I draw the protons over here. Now, protons on the beta carbon, that is the next carbon. In which of these two cases do you have a Br anti-periplanar to the proton on the next carbon? The first one. Which one? A or B? B. So the TBUOK will pick up this proton. This kicks out. Over here, do you have an anti-proton to this Br? Do you have a proton on the next carbon which is anti to the Br? Which way is the Br pointing, up or down? Down. So do you have a proton on the carbon that should be, if it's down, the anti-proton should be up. Do you have a proton on this carbon which is up? We have. But being anti is not sufficient, anti-periplanar, right? So that's why this is a good problem, because it reinforces both the points. You have to be anti and periplanar, anti on the same plane. What did we have a syn periplanar elimination yesterday? Benzynes. So this is not as good. For this to eliminate, what you have to happen is this ring has to flip. All right? Let's not go into all that. Just for now, we know this is like locked up in an anti-periplanar conformation. This is not. Therefore, that's easy to eliminate. All right? Everyone gets this problem? Okay, let's look at the next one. Yes?
So I understand the part that on the left side,
Mm-hmm.
because
Mm-hmm.
that's why it works. But second one, I know it works, but why is left one is better than...
So anti-periplanar means they have to be 180 degrees, right? Are these 180 degrees? No. This is pointing down. 180 with that will be like this. Get it? This is not 180. What angle is that? I'll let you think. It's 60. Okay? Now, this next problem, what does this next problem test you on? Can I erase this thing? You guys don't have a question, right? What do you do when you have a question? Dial 911. No, ask. That you can do an elimination once again. This is a base, not a nucleophile. We'll take it for granted for now. We'll see later why it's a base and not a nucleophile. Now I will pick up a proton, right? Proton from which carbon? From that carbon, or how far should that carbon be where you pick up the proton from? Adjacent, right? It's called beta elimination. That's alpha, that's beta. That's also beta. That's also beta. So if I number these carbons 1, 2, and 3, which of these carbons, first of all, which of these carbons have a proton? Does 3 have a proton? We would not do an elimination here, right? What is called? If you do an elimination here, what is that called? Outrageous. Right? 1 and 2, which one would you pick up a proton from? Why? What's the rule? More substituted alkene is what I want, right? Zaitsev elimination. Should pick up from this carbon. Get it? Say it one more time. Sure. Fast or slow? Slow. So you pick up a proton from that carbon, which gives you the more substituted alkene. I would say it's from that beta carbon, all right? More substituted alkene. Or alternatively, you can say pick up a proton from the carbon which is more substituted. Okay? Yes.
Even though it's second order, it doesn't matter if it's an E2 reaction. You said less is more substituted. What would be more substituted?
I didn't really.
So even though it's a second order
Uh-huh.
reaction, it doesn't matter if you have an E2 reaction, it'll want to go to the more substituted.
No, I mean, it's an E2 there for second order, right?
Yes.
So, I mean, and that will happen such that your transition state is more stabilized.
So even though it's more hindered,
It's more hindered, right? We will have, yes, it is more hindered, but even then it's better. We will have the otherwise, which is called the Hoffman. We do not need that now. For now, we'll make that alkene, which is more stable. Yes?
Can you go back one slide? Isn't that base taking it from the lesser substituted?
This carbon has 1, 2 groups off it, right?
Yeah.
This one has 1 on it. Oops, this one. So leaving group, alpha, 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 right?
Yes, it's more.
So more substituted in terms of what? In terms of the carbon it's attached to.
So more substituted only means carbons.
Only means carbons. Just like here, more substituted. This is more substituted. That means that more carbons, not more hydrogens. Yes?
Can you explain the alpha versus beta again?
Alpha versus beta? Right, alpha, so this is a way of naming it. All right? Alpha means the carbon where your leaving group is attached. Beta is an adjacent carbon. All right? So this is how you keep track. You know, when I used to do this, I used to get it wrong. Right? I used to take up from the alpha, beta, gamma, all the Greek alphabets. No, just take it off from the beta carbon. So the first thing you do is find out which is beta, and you eliminate, and then you find out which beta is more substituted. Then you eliminate from that. If you don't do that, you probably try to eliminate from here, get you confused in the exam, or from here if it had a carbon, if it had a hydrogen. All right. So first mark them as beta and then find out which is the lowest number of hydrogen or highest substitution. All right? So how is the product going to look like? I don't mess around with the benzene ring, right? That stays the way it is. This, that, and that. Where do I form the double bond? Between carbon 1 and 2, 1 and 3, 1 and 4. 1 and 2, like that. Clear? One more problem that stresses on anti-periplanar is question 3. That was on your homework. Do you want me to go over it? Mm-hmm. Okay. So you can do an elimination, and you want the product, which is the best product. So the BR, let's see what's the problem. Now, first we do is alpha beta, right? Yeah. That's my leaving group. That carbon is alpha or beta? Alpha. Next carbon is beta. That's a beta, that's a beta. How many protons do you have here? 1. How many do you have here? So now, Zaitsev elimination can happen from either side. So now we can look for something else, which is which carbon would be which carbon would present you with an anti-periplanar proton, all right? So to do that, we have to do what? Draw up the cyclohexane in its full glory. Where would you put the tertiary butyl, which is that group? Equatorial axial. That's pretty bulky group, right? You want them minimized to minimize the energy. So you put that? Equatorial. Everyone gets it equatorial? All right? Now, I'll number these 1, 2, 3, and 4. So if that's 1, that's 2, 3, and 4. And you should also do that. That helps you keep track. On carbon number 2, what do you have? A methyl. How is the methyl pointing? It's with relation to the T-butyl. Is it pointing cis or trans? Cis. So would that be pointing up or down? Up on this carbon, is it axial or is it equatorial? When the carbon's pointing up, axial bonds point up, all right? That's what the methyl is. And the hydrogen, therefore, is? Equatorial down. Number 3 has a BR. BR is trans or cis? Trans. Trans means if this is pointing up, the BR should be pointing down. Down is axial or equatorial? Axial. The carbon's pointing down, axial bond will point down. You know how to draw it? Ask me if you don't, we'll go over these rules once again. Carbon 4, this methyl is pointing up or down? Down is axial or equatorial? Good. Now we'll see which of these carbons present an anti-periplanar proton to this Br. Carbon 2 or carbon 4? 4 does. Therefore, a TBUOK comes in like that, that, and that, and your product looks like this, which can also be drawn as that 1, 2, 3, and 4. 1, 2, 3, and 4. 2 has a cis methyl. 3 has a double bond onto 4, and 4 has a methyl. That. Okay, that is how you reach the answer. Get this? How is the methyl on 4 will go? I was going to ask you that. Is this carbon, what's the hybridization of that carbon? sp2. That means sp2 carbons are the tetrahedral. They're planar, right? So it will point like that, just like that, in the same plane as this hydrogen. So you don't need to show it up or down, all right? Can we move on to number 3? Conformation. How do you draw it? You draw it as a, you know how to draw a cyclohexane, right? Chair. The bulkiest group should stay equatorial, first thing. Second is, you want to draw the cis. Cis over here means pointing upwards. So you have to know how the upward group is going to be like. Whenever you draw a cyclohexane, the carbon, the axial groups point the same way as the carbon does. Is this carbon pointing up or down? Up, right? Axial group will point up. Okay? And once you have the axial, the equatorial will be easy to draw. Get it? All right, now, yeah.
I have a question. What if the first one that you draw, what if that is not bulky? How can you
What is that not? If that's not bulky, it will be more bulky than the methyl, than the Br. Otherwise, that question will not be easy to answer. All right? Try to put it equatorial. Okay? Now let's look at question number 3. No, question 4. Question 4. Now, this is the alpha carbon. That's a beta carbon. That's a beta carbon. That's also a beta carbon. I'll draw out the phenyl. Just because I drew it out like this, don't let this bias you. Which of these beta carbons have protons that you can eliminate? 1, 2, and 3. And which is the one that you can take the proton out from? Because It's not anti yet, but you can rotate this. The first thing we'll look for is which has protons, and then we'll see where we can apply the Zaitsev rule. Zaitsev rule between 1 and 3, which one will work better? 3 is more substituted, right? So now we have to put 3 anti-periplanar with this iodine. How will you do that? Turn this. Everyone get it? Iodine. Phenyl. So if I have to draw an anti-periplanar, where would I put the proton? On the plane of the board, up or down? Up and on the plane of the board. Anti-periplanar means on the same plane. The proton's up in the plane of the board. Where is this isopropyl going to point? Up, outside or inside? So I push this in, right? If I push that in, this will turn, and this isopropyl will rise up from the board or go in. And therefore that goes down, but it's not by so much that it will also point out. This goes down and still stays in. Like that. Okay? Do you get this rotation? Yes.
I had a question on the question before.
On this one?
Yeah.
Uh-huh.
Pineapple,
This?
yeah.
The T-beetle? Yeah.
Is it pointing up at us or down or in plane?
It's in the plane of the board. It's in the plane of the board. This bond is coming out. This bond is going in. Okay? When you draw cyclohexanes, these two bonds are on the plane of the board. So if I draw the product of this reaction, now you can see the beauty of the E2 reaction is this picks up that proton, this ends up, that goes out. I have the double bond like that. pH is cis with which group? The isopropyl, right? And it stays cis in the product. So since once you put it in an anti-periplanar arrangement, whichever group was cis will end up cis.
In the product, is it okay if we just draw that, but with the leader group gone and a double bond?
Yeah. That will look bad, but it's still all right. That. Yes.
Do we have to have the phenyl and the
Phenyl and the ethyl? Like, what do you mean?
oh wait, so that the ethyl comes out?
The ethyl's that. This is the isopropyl. They are cis, right? Basically, you're forming a double bond.
Do they push down because
They both come to the plane. So one is pointing up, one is pointing down like that. They come down, come up like this. Okay. So now they're in the same plane. Those two are in the same plane. Do you get this presentation? It kind of looks like this. After that, this looks like this. Double bond. These two are both pointing out, and they still point in, out, pointing in, pointing in. Do you get this better? Yes, don't say no. All right, that's why you get only one product from an E2 elimination and not multiple products. Yes? Rotation? Like from here to here? So you take this, you keep this carbon constant. And like a wheel, all right, you move this axis into the plane of the board. Say I push this hydrogen on the plane of the board, right? That means I'm going into the plane of the board. And it's going to turn like this. As that happens, this is going to push up. That's pushing up. This was out, still stays in, but goes down. How would I show it? This was how your wheel was. You move the H in, this will move down, this will move up. All right? Yes.
I thought that if you double bond, you couldn't draw stereochemistry.
This is yeah. So you don't need stereochemistry, but this is when I draw it flat on the board. This is when I give it to you on a plate, like on a platter, like that. So it's not really stereochemistry. It's just saying that this alkene is on the plane of the board. This is pointing out. That's pointing out. That's going in. That's going in.
More so like, could you put that as an answer for the exam, or do
Yeah.
you want the other one?
Yeah, you can. Both of them are right. Clear? Yes.
Should it be the ethyl?
The ethyl?
No, I mean, before the rotation.
Uh-huh.
Should the ethyl come out?
Before the rotation?
Yeah.
No, you're pushing the hydrogen in, right? So the ethyl will not come out. It will just go downwards. So this is how it was. These groups were like this. H, ethyl, isopropyl. You push the H on the plane of the board. The ethyl is still in, but down. The isopropyl is out and up and down. Get it? All right. Yeah. Okay. Can you move on? You can try a model with that, all right? So let's find out how to decide. So we understood that SN2 and E2s are most favored, right? Whenever you have a reaction, you would pick up SN2 and E2. Why are SN2 and E2 favored over SN1 E1? Because number is bigger, second order. The reason is bond breaking is compensated by bond formation, right? That's why SN2 and E2 are favored. Now, since these are favored, which one would I pick? So this is, say for example, this is my substrate. This is an alpha proton, this is an alpha carbon, that's a beta carbon. So you see, if I pick up stuff from the beta carbon, that's an elimination, right? If I attack the alpha carbon, that's a substitution. If you have a bulky substrate like that, you would prefer to pick up a proton from the periphery than to attack on the carbon. So to decide between SN2 and E2, see if the substrate is bulky or not. If the substrate is bulky, you would do an E2 rather than an SN2. So if it's by bulky, I would mean this center should be tertiary. Let's look at an example. So So we're trying to decide if it's an SN2 or an E2. That thing can act both as a base and a nucleophile. That's a methoxide. Now, what is this substrate? Bulky or not bulky? Bulky, because this carbon is tertiary. So this methoxide will have a hard time getting in there. You see, if I draw out all the hydrogens, how hindered that is. So what will the methoxide do? Pick up one of these protons. All right? As a result, you get this alkene. So if you have a tertiary substrate, then E2 will take precedence. If it's a good base, or a good nucleophile. Now, what is this? A secondary, primary, tertiary? Primary. That will do a SN2, all right? Now, what would you do over here, the last substrate? Elimination or substitution? Elimination, raise your hands. Substitution, raise your hands. Why would it not be elimination? Because it's primary. And second is, if you want to do an elimination, do you have a proton over here? No, you don't have a beta proton, right? It's primary at that center, therefore substitution, and also no elimination because there is no beta proton. So when I say primary, secondary, tertiary, I mean the alpha carbon. Not here, not here. That. Get this first point? So SN2 and E2 are favored. Now we just learned how to decide between SN2 and E2. One more thing we have to learn to decide between SN2 and E2, and then we'll do a lot of problems where we'll have to decide which is it. Let's move on.
Are we going to do an example where there's a secondary carbon?
If there's secondary carbon, then you can have both SN2 and E2. All right? So those are not clear cut, and you will not be asked on those. For an SN2 and E2, whenever you see that when this A minus is an anion, all right? An anion can act as a nucleophile as well as a base. When your anion picks up a proton, what do you call that? Base. When the anion attacks that carbon, it's a nucleophile, all right? So to have an SN2 reaction, what do you need, a nucleophile or a base? Nucleophile for SN2, and for an E2 reaction, nucleophile or base? Base. So now we're going to see what makes something a good nucleophile versus what makes it a good base. Usually for a given atom, nucleophilicity and basicity parallel each other. All right? Say for example, between these two. So whatever is a good nucleophile would be a good base if it's the same atom. These slides, by the way, are modified. I'll send them to you. This might not be this way in the slides that I sent you. You'll get them tonight or maybe tomorrow morning, all of the modified slides. So between these two, you see what's the basic atom in both these examples? The carbon, hydrogen, and oxygen. Like who is going to attack? Say I have a substrate. Say I have this substrate. All right? And I have which of these two, what would attack? The oxygen will attack, right? Which of these two is a stronger base? Because of minus, negative charge, higher charge density. That is a strong base, that's also a strong nucleophile, all right? You can't do much about this. So these are borderline cases. We'll see when we can make a clear-cut difference. When it's a borderline case, you'll get both the reactions happening. You would not be able to give a definite answer. That versus, you see both of these are negative. Why was this a better base? Because O has a negative, right? In this case, both the oxygens have negative. Which is a better nucleophile as well as better base? So a good base would be willing to give away its electron or not willing? Willing, because it wants to use its electrons to pick up or steal a hydrogen, right? So is this lone pair available to pick up electrons or high protons? Because it's more busy in traveling, right? Resonance. This lone pair is more confined, so it would like to pick up a proton. So that's more basic, therefore that's more nucleophilic. So when you have the same atom, so if you want to compare between the same atom as being more basic and nucleophilic, usually basicity parallels nucleophilicity. All right? Now what happens is, if you're going to compare between two atoms, so between these two species, the first one is a better base as well as a better nucleophile. This same here, the first one is a better base as well as a better nucleophile. However, when you're comparing between atoms, all right, as you go from left to right of a periodic table, the base gets worse and the nucleophile also gets worse. That means CH3 minus versus NH2 minus. Which is a stronger base? Stronger bases have their lone pairs available or less available? More available. If it's more available, would the atom be stingy and holding on to it, or would it be more open-minded? It's going to be willing to give, right? Which one is more philanthropic? Like willing to give the electrons away. This, right? More basic. And therefore, more nucleophilic. Now, how are carbon and nitrogen related on the periodic table? They go from left to right. All right? So if I had oxygen, the trend. Now, as you go from top to bottom, all right, that's when the game gets much easier. As you go down, your bases get worse and worse, but the nucleophiles get better and better. Therefore, if I'm comparing OH minus and SH minus, which is more basic? OH is more basic. Which is more nucleophilic? More nucleophilic. So OH will give you an elimination or substitution. Bases give you? And nucleophiles give you substitution, right? So OH will give you a elimination, and SH will give you? And what kind of elimination am I talking about? E1, E2? What kind of substitution am I talking about? E2. SN2, sorry. So we are still in the second order. We have not looked at first order because first order is rare, doesn't really happen unless I force conditions on them. We'll see what those conditions are. Yeah.
Which one did you say was more overpowered, going left to right or up and down?
So when you're comparing atoms like that,
Yeah.
this is what the trend is. When you're comparing
Between carbon and say like I don't know,
carbon and silicon
or
and sulfur,
nitrogen
nitrogen
and sulfur.
and sulfur. Nitrogen is more basic, sulfur is less basic, more nucleophilic. So yeah, going down will be more overpowering for now. All right? But you can't use that all the time. I'll say sulfur is always a good nucleophile. All right? So here is the trend. For the elements in the first row, like oxygens, all right? To make them good bases, these are exclusively bases, all right? You see how bulky they are? Because you make them bulky, it makes it even harder for them to reach the carbon, and they'll pick up a proton. So bulky bases, bulky anions, would rather be bases. If they're not bulky, they can act as both nucleophile as well as base. That's what we did in the problem that we just erased anyhow. If they're not bulky, these two can act as both nucleophile and bases, all right? These, by the way, will act exclusively as nucleophiles, never as bases, all right? So if you want to do a distinction between E2 and SN2, what do you need? SN2 is preferred by what kind of substrate? Bulky or less bulky? Less bulky. Second thing is basic nucleophilic. These will give you a E2. These will give you SN2. This thing will get clear as we switch on to these problems. All right. Let's do these problems. This is from the homework, exactly. Let's do problem number 1. So I want to look for SN2 reaction. SN2 reaction with this substrate. You see, although SN2 is mentioned, this substrate will tend to give you what? SN2 or E2? What do you think of first when you're looking at the substrate? Bulk, right? Is the bulky substrate bulk with reference to this carbon? Is it primary, secondary, tertiary? Primary, right? Primary substrate preferred to give you SN2. So even if you did not have this word over there, you should be able to tell that this substrate gives you an SN2. Now we'll choose which of these act as the best nucleophile, which acts as a worst nucleophile, okay? All right. So which is the best nucleophile? Let's look at this trend. And I'll list these on the board, and you look at the trend. Okay, now let's look at the trend and use it. A, B, C, D. So what's my best nucleophile? D is the best nucleophile, right? Yeah. Because we are comparing between atoms. And between atoms, sulfur is always the best nucleophile. So I'll put D as the best nucleophile. D is better than all these, right? Now, all these, which is the nucleophilic or basic atom? Oxygen. How do you compare the same atom? More basic is more nucleophilic, right? So if I want to compare all these, whichever is more basic is more nucleophilic. So between A, B, and C, which is more basic? Which is least basic? Because that's not charged. Okay. So I'm left with A and B. Which is more basic? B is more basic. Therefore, that's more nucleophilic. And that's A. Do you get how to do it? Yes. Why is more B nucleophilic than A? Than A? Because B, this negative is confined on this oxygen, right? Over here, this negative is in a p orbital and it travels around. Right? Yes. C is the least basic. Because when you're comparing the same set of atoms, least basic is least nucleophilic. That's why it's least nucleophilic. Okay. Everyone gets this problem? So we are still on the second order reactions. We'll move to first order later after we get done with these. Now, next set of problems. What do you want here? The problem tells you want a elimination, right? You see the base that's being used? This base can also act as a nucleophile, right? So basically, this problem uses an anion which can act both as a base and a nucleophile. So it wants to use your idea of substrates, or what you understand about substrates, that will give you the best, that are best for elimination. Get it? So your nucleophile is fixed, or the base is fixed, and the substrates keep changing. To get an elimination, what kind of substrate do you want? Primary, secondary, tertiary? Bulky the better, right? Which are the bulkiest substrates? C and D. So C and D are the best, and they're better than A and B. Okay. Between C and D, which is better? What's the difference? The leaving group is the one that's different. So which is a better leaving group? I is a better leaving group. So C is better than D. Which are better than? Between A and B, which is a better leaving group? BR is a better leaving group. Yeah.
What is the difference between leaving groups? Like, why is one better than the other?
So leaving groups usually are stronger acids, stronger conjugate bases. Conjugate bases of stronger acids are better leaving groups. So you can write this down. I'll probably include this in the slides. Conjugate bases of strong acids are good leaving groups. All right. Conjugate bases of stronger acid are good leaving groups. Clear over here? We can tell yes.
Then why would fluorine be less than bromine?
Fluorine is a really bad leaving group. It's one of the worst leaving groups, right? It's like Teflon. Teflon is all fluorinated carbon, all right? Hydrocarbon. Fluorine forms a really strong bond with carbon. You can never get it to leave. Yes. Sorry? Sorry? Conjugate base of a strong acid is a good leaving group. Fluorine, I would say, is an exception. By HF is not a strong acid, by the way. HF is a weak acid, and that's why it's a bad leaving group, right?
So
Yes.
HI is a stronger acid than H.
BR. Yeah, HI is a stronger acid than HBr.
Is it stronger than HCl?
HI is stronger than HCl. Yes.
Can you explain again, like when you first looked at the problem, why you decided?
What we are doing in the first step, coming to you. First, I'm trying to see what kind of reaction I have to look at, right? Because if this problem asks for elimination, for substitution, the trend will reverse, right? The trend will be something else. It is asking for elimination. Now I'm trying to think, elimination. What elimination is it? E1 or E2? E2 elimination, right? Because I'm having, we'll see why this is an E2, but let's take for granted this is an E2 elimination, all right? then we should think about what kind of bases give you, or what kind of substrate give you a better E2 elimination. Why substrate? Because the base over here is constant, right? The base is the methoxide. That's constant. The substrate is changing. So what substrate gives me the better elimination? First of all, tertiary substrate give me a better elimination, right? Because if it was primary, it will give you a SN2 sort of reaction. So these two will be the best, and they are in one group. These two the worst, then the second group. Between these two, the only difference is the leaving group. The better the leaving group, the faster the reaction. Between those two, once again the difference is the leaving group. Better the leaving group, better the reaction. Get it? The explanation, people like my explanation. All right, can we move? Yes. Sorry, yeah, please. No. The better than nucleophile? Yeah. So if it's the same atom, right? If you're comparing the same atoms, stronger nucleophiles equal stronger bases. If it, say for example here, all these are oxygen, right? So strongest base is strongest nucleophile. But the moment you're comparing oxygen and sulfur, that's when you have to use this chart. Okay? Now what we have been waiting for, the first order reaction. So what causes first order reaction? So let's look at the features of first order reaction. First order reactions are kind of a relief because in the first order reaction, you see it's a two-step process. The first step, you form the carbocation. In the second step, you can either have this nucleophile attack the carbocation, giving you the product, or you can have this thing, the anion, act as a base and give you the elimination. What's the slowest step, the first step or the second step? First step is the slowest. And since both these processes, the first one is an SN1, second one is an E1, share the same intermediate, therefore once you form the intermediate, both of these will happen. That's why SN1 and E1 will compete. All right? Unlike SN2 and E2, where it go through, okay, which one is going to happen, the larger size of the substrate, which is more nucleophilic. SN1, much easier. If you're seeing it's a first order condition, you get both SN1 product and an E1 product. Get it? Makes life simple, right? That's how it should be. Now, this first reaction is my SN1 reaction. See what's going on. For SN2 reaction, how many isomers of the product did I get? One, good. For SN1 reaction, we'll get all the isomers of the product if it happens to be chiral. Why? Because, and that's what I tried to point over here, these two are, how are these two related? Enantiomers, diastereomers? This carbon is a reflection of that carbon, right? Is this carbon a reflection of that carbon? So these two carbons are reflections of each other, right? If this was R, that would be S. The first carbon, are they reflections? No, the same, right? H is pointing back, these two, the same order. Therefore, if this is S, that should be S and S. So I have two compounds with configurations of SR and SS. What do you think they are? How are they related? Diastereomers. All right? Second one, how are these two related? Cis and trans alkenes are, or easy alkenes are? Diastereomers. Right? So you're getting a mixture of isomers in the first order reaction, not same product. Why do you get these mixture of isomers? Let's see. Let me pick up that this starting material. Have a iodine as a leaving group. That. Now, for an SN2 reaction, the nucleophile attacks from the backside, and that's what caused the leaving group to go away. SN1 reaction, or first order reaction, that doesn't happen. This bond breaks first, and that's why it's unfavorable. You form a carbocation. Carbocations are planar. Now, your nucleophile can attack the carbocation from either of the faces, right? You have two of the faces exposed. Your nucleophile can come from this face or it can come from the other face. Therefore, if it comes from that face, you would get a nucleophile that. Comes from the other face, you'd get that. See that? You're getting both the isomers. How are these isomers related in this case? Enantiomers or diastereomers? Enantiomers, only one chiral center. Okay. Same with the elimination process. Let's take this. So, first order process, this I leaves. So this H will donate and it will form the bond, right? This CH bond will donate the electrons to form the pi bond. But this is a chance of rotating. If it does rotate, this is how it's going to look like. Right, I rotated that carbon. Does everyone have finals next week? No, I guess not. I thought only grad students don't have final. We have finals every day. So you see, if you do that, and you can do that. If you do this, you'll get one of the diastereomers. Do that, you'll get the other diastereomers. You can go home and work on that. So that's how you end up with both the diastereomers for the alkene. This will give you the alkenes, and this gives you a substitution product. So E1, both the diastereomers. SN1, both the diastereomers and enantiomers. Yes?
What causes the rotation?
Because this is a single bond. So just room temperature, the heat, the kinetic energy. So if we got this thing, let's try the problems. Did we get this thing so far? All right. See which page I should do first. Yeah. So I'll have this chart open. I'll list the problems one by one, and I'll have this chart open. It says that how to decide the reaction mechanism. This is like a schematic, all right? Now anyone from computer sciences would probably be angry because this is not how a decision box should look like. But this is a 3-pronged, 5-pronged decision box, all right? So first of all, you start off with the default that this is an SN2 reaction. And you look for factors that detract you, all right? So is it a strong base or strong nucleophile? Yes. It's a strong base, you'd get what? E2. It's a strong nucleophile? SN2. If it's none of that, that means you have a solvent, which is, say, for example, methanol. Methanol is not a strong base or nucleophile. It's a neutral species, right? Therefore, you would get an SN1 and SN2. No need to make a decision here. SN1 will happen. SN2 will also happen. SN1 and E1, exactly. Yeah. I'm getting carried away by the people next door. Right. If it's a borderline, what do I mean by borderline species? It's not. It's like it's one of these. All right. It's strong, but I don't know if it's a good base or a good nucleophile. If it's a borderline species, I'll see if the substrate is bulky. If the substrate is bulky, what would you get? Bulky means tertiary, right? Substrate is not bulky, that is primary, you get SN2 mainly. Mainly is the important part. If it's secondary, you can get both. You would not be tested on something that ambiguous. Sure. Confident. Now, let's do these problems. Before we do this, let's do the, which problem should I do first? Let's do problem number 4 first. Right? That's important. Why is that important? Because it will make us nostalgic. This is something we had on the 3rd exam, right? And got wrong. I like nostalgia. Wiping the tears. All right. Let's see. That reaction, is this a strong base or look, let me put this down here and I'll keep the, oops. What does reflux mean? Heat, exactly. Now, let's have this chart open. First of all, by default, we'll think about SN2, my chalk dropped. And then we'll look for factors that detract. Is it a strong base or strong nucleophile? What would you say?
No.
Why not? It's a neutral species. It's a solvent, all right? It's methanol. It's not a strong base, not a strong nucleophile. So what would you get? SN1 and E1. So if it's an SN1 and E1, because the first order will give you both of them, SN1 would be, what will I put here? OCH3. And E1 would be? You would form the carbocation, but you would not isolate the carbocation. This is your final product. This does go through a carbocation, like it does form that, which is, you're right. But you would not isolate that. This goes to the product. Okay? Now, let's now start off by looking at problem number 1, which is also in the homework at some point. So I'll give it a raise. Okay. Number 1, what kind of condition is that? So you're taking what? It's a strong base, strong nucleophile? Weak. So you'd have a first order case, right? Which means you'll get both SN1 and E1. That's why we asked draw the substitution product, because we know it's a first order, therefore you get both SN1 and E1. So how many substitution products would you form? Exactly, let's see. Let's see if I know the answer, right? Because I would not have the privilege of taking the exam on Friday. So, SN first order, right? And I'm drawing the substitution product. Where is your, which carbon would you do the substitution on? The one with the iodine. Would I make this mess with the stereochemistry on that carbon? What do I do on that carbon? It goes via carbocation, right? Therefore, the methanol can come from both top and from the bottom. As a result, get that, as well as that. How are these two related? Diastereomers. AJ, can you see it? Or do I need to magnify? Diastereomers. That's the second answer. How is the isomeric relationship between these two products? Yeah. This one? Number 4.
When you said the carbocation,
Yeah.
when you form, wouldn't it do a hydrogen shift to make a tertiary carbocation?
This is benzylic, right? Benzylic. So that's also pretty stable. That's also pretty stable. I mean, your questions you'll get will be less ambiguous. But this is an example where we try to stress that SN1 E1 will be favored. I mean, both will be favored. All right. Now, let's look at problem number 2. How do you get that? What's the purpose of NaH? Nah. What does that do? Acts as a nucleophile, or? All right, I'm not looking. You can give me the wrong answer if you want.
But isn't it NaH is a good base? So
Good base, exactly. Good answer.
is it E2 though?
Good base. So it picks up a proton. We'll see what happens next. All right. Good base for the proton. All right. And we did this problem before. And Sarah also did this problem for her homework. I don't know where Sarah is. That's where I saw it. I liked it. What happens next? That comes here. Is it? Are you eliminating or are you substituting? You are, for this carbon, you're exchanging his bond with an iodine with the bond with the carbon, right? So that is substitution. What kind of substitution would you have, SN1 or E1? Do you have a real negative doing the substitution? That kicks in here, right? Now, does this iodine leave first, or do you make it leave? You make it leave, and when you make it leave, it's called? For the sake of an exam on Friday, let's have an answer. SN2 or SN1? SN2, you're right. That gives you the product. Okay? That's a primary center, right? Primary center. What do you want?
But we said it was a good base.
That was a good base.
But it's not
That good base now gave rise to a good nucleophile.
Oh.
Is that beautiful? You see they're clapping. Get that? All right. Now let's predict the mechanism for question 3. Can we move on? Yes.
So every time we have a nucleophile being made, we know it's going to go, and with the benzene being what's going to go to benzene.
Oh, I can't talk about every time, but this time it is. All right? Yes. This time it's a good nucleophile. Now, predict the mechanism for this reaction. Yeah, question.
The example above,
Uh-huh.
is there still a methyl there? Or I mean,
Over here? Yes, there's a methyl, but I didn't draw the stereochemistry because this carbon is flat.
I mean when it has the,
Yeah, the methyl should be at the back. I'm sorry. You're right. And now it's in the front. Exactly. All right, next problem. Say you have the same substrate, right? And secondary substrates are not primary, not tertiary. Therefore, they can give you both SN1, yes.
Oh, why is that SN2 again? Can you explain it?
Because I have a strong nucleophile. Right?
Yeah.
Because I have a real negative charge doing the substitution. Yes.
Back for number 1,
Uh-huh.
were we supposed to get 2 E1 products as well?
E1 product, you'd get one over here between this carbon and that, right? That's minor. These two are equally substituted by Zaitsev rules. You'd pick up proton from here and from here. Those two are also 2 more products. You get 3 products. Wow. Well, we'll do one problem like that. We'll see one problem like that. Now, let's look at this question. Can I erase this thing? Okay, you get the same product. You get the same product from the same substrate. So this is your substrate. And you subject this substrate to the two different conditions, giving you the same product. What kind of pathway are you going through? Let's figure out. By default, we'll think of SN2 and then we'll look for detracting factors. Is it a strong base or strong nucleophile? Strong nucleophile. It's not an elimination, is it? You have a substitution for sure. So it's a strong nucleophile. So what kind of mechanism are you getting? SN2. Get it, everyone? Strong, no? How do I know? It's negative charge, negative charge. Now, why did I pick up this substrate? Because if it was primary, that will force me to do a second order. Is this a strong base or strong nucleophile? It's a bad nucleophile, right? Therefore, SN1, good answer. Does everyone have the same answer? Get it? Yes. Do you want me to come in the picture? Yes. Can it be? It's not E1. I mean, you're given these products. If you're not given this product, you would get an E1 with the SN1. But the question has these products included. You see that? The products are included. So therefore, you're looking at the product and thinking, okay, the product is a substitution product. Is it first order or second order? So we are done with problem on this page. Let's move on. More problems. Wow. Are we lucky? Do you want me to go over these problems or do you want me to skip? Because these are all from your homeworks. Let's do problem. Let's just do this problem, right? The rest we know how to do it. Just look at problem number 2. Yeah. It's from the homework, yes. What?
I never seen it.
Oh, you didn't do this on the homework? I gotta take points from you. I'll go back. Now, on question number 2, what kind of condition is this? SN1 E1 SN2 E2? First order, right? Good. So first order conditions give you what? A carbocation? We're doing number 2. How do you know it's a first order? Because it's not a strong base or a strong nucleophile. And it has reflux underneath. So you would generate a carbocation. This is what I wanted to point out. That's where I'm going after this thing gets over. For first order reaction, you run the risk of doing what? A carbocation rearrangement. All right? Second order reactions, no carbocation, no rearrangement. All right? First order reactions, carbocation rearrangement. That's what you had written down over here, carbocation rearrangement. We have kind of stressed on all these points except for this one. That's why we're picking up this problem to stress on that point. So this carbocation, what kind of carbocation is this? Primary, secondary, tertiary? Is it stabilized by resonance? Does it have a future? Oh, it does have a future. It does have a future. What does it do after graduation? Does a methyl shift? Even carbocations like to be optimistic. That. Now, is this carbocation any better, and for what reasons? First of all, what stabilizes a carbocation best? Resonance. Does it have resonance? Yes. With what? The benzene rings, all right? Phenol with the benzene with an OH. So phenol. Let's say benzene rings. All right? And what else is good about this? Is primary, secondary, tertiary? Tertiary. Tertiary with resonance. It has a great future, all right? Water. What happens next? Water again. All right? Water, water everywhere. And that's your PDKT, not drawing it out again. That means product. Okay? So, let's look at the general concerns. What are the general concerns? That is, allylic benzylic substrates favored first order mechanisms. What does that mean? And why? First order and second order mechanisms. Say. What kind of condition is this? First order, second order? First order. It's a carbocation. Why is this carbocation? Why is this favored? Why is the first order reaction favored? This carbocation is stable, right? For what reason? Resonance. So that's why first order is favored. Second order will be, I take this, Na plus. We'll do a backside attack. Let's draw the transition state. This transition state is stabilized by this pi bond, all right? These p orbitals. So both first order and this is second order are favored if you have an allylic. Benzylic would be having a benzene ring over here, okay? So both those are favored. We'll see more problems of this. What? No, there will be a printed question. So if it asks you for an answer, there will be definitely a question before that. Reactions of sp3 carbon, all right? So SN2 reactions for what carbon? sp3, all right? sp3 carbons for SN2 reactions. If you want to do a substitution on a non-sp3 carbon, what do you use? Cuprates. Let's look at this problem. You see that? That's an iodine. And you did a substitution. What was the reagent over here? Up. Do you want this? Tilt the board? You can see what? Never mind. All right. Say I want to do this, all right? I want to do a formal substitution. Formal means in formality it looks like a substitution. You see that, a substitution? By the way, it's not from the, it is not the backside substitution because the phenyl ends up on the same side as the iodine. It's not on that back side, all right? It's not trans. So that's something else you should notice. I did something that looked like a substitution on an sp2 carbon. What is this reagent? Cuprates. I passed the exam. All right? That, very important. And it does not end up trans, it ends up cis, whichever way the iodine was pointing. Yes?
So can you explain why is it cuprate instead of
MTBR will not do this reaction. Now, why it does not do it? That's more involved. All right? If you take an organometallics course, I'll be able to tell you better.
And then, like, can you show me mechanism?
The mechanism of this one? That mechanism I can show you, but it's a wrong mechanism, by the way. I'll tell you that.
Oh, really?
Yeah. Because this is how the mechanism is shown. That's wrong. You'd never do an SN2 even like that. The copper has d orbitals which interact, which break into sigma bond, right? That's an insertion, right? So better not be confused. Life is simple. Let it be like that.
Yeah, because on the exam 3, Funk has to.
Exam 3 is passed. All right. Now, this is one more example where you have what? What is this going to do? What is this reaction? SNAR. Nucleophilic substitution on an aromatic ring. So these, why did I put these up? As an exception to this rule. That reactions on sp3 carbon, that means substitution, can happen only on sp3 carbon, except for these two cases where you get a formal substitution on an sp2 carbon. This is so deactivated that this nucleophile can actually go in and attack here. This is the the nucleophilic substitution on a benzene ring. That's the only case where it will happen. It needs to be extremely deactivated. All right? So remember those two problems. Cl will not happen if it's just a Cl. You need to have electron withdrawing groups like that, which will be able to stabilize your negative charge from the incoming nucleophile. That, and that. That's why you need this motif to do all that, all right? What happens next? Kicks in, out. Okay? That. Okay? So you did sort of a formal substitution on an sp2 carbon. You see the Cl is gone and you have a methoxy over there. So these two examples are important. They're exceptions. Yes? These nitros, I made this substrate, right? So you can have a substrate made whichever way you want, but unless they're ortho, you would not be able to move these pi electrons into the nitrogens, right? If they're meta, by no way of resonance would you be able to push the pi electrons into nitro that's meta. They need to be ortho and para. Okay? So it's a nucleophilic aromatic substitution reaction. Now, going to problem number 1. What do you think this problem number 1 is? Is it a SN2 SN1 E1 E2? SN2. All right. Is it a second order, right? Why? Because this is a good anion based on nucleophile. I cannot decide if this will act as a base or a nucleophile because it's borderline, right? Can you do an E2 on this carbon? Why not? You don't have an alpha proton, a beta proton. So this is a borderline species, gives you both SN2 and E2. But since you don't have a beta proton, you would end up with SN2. Okay? Question? I'm waiting for people to write this thing down before I can erase it. For cuprates, the formal mechanism is the whatever was done in class, the copper minus adds onto the, it does an SN2 sort of thing. That's not really right, but we'll take it for 210. So, are we done copying this down? Let's do problem number 4. Problem 4. You have this reaction happening, all right? And asks you, select the best conditions for this following reaction. Now, what reaction is this going from here to here? Is it an elimination or substitution? Substitution. That carbon is primary, so you would have an SN2 or an ESN1. SN2, so you need an SN2. So basically, you first decide what the mechanism is of this step, right? It's a primary carbon, so it's second order, and you look at the product, it's a substitution, so it's an SN2 reaction. Now you will look at these and find out which gives you the best condition for an SN2 reaction. CH3OH reflux, best condition for SN2? No. CH3ONA and CH3OH. Strong nucleophile, but is this a good solvent? What kind of solvent do you need? Aprotic. Do you know what aprotic is? Aprotic means you would not have a bond between a hydrogen and an electronegative atom. Electronegative means anything more negative than carbon, like nitrogen, oxygen, all right, chlorine, etc. So you do not have any bond like that, right? That's why. So you need, say for example, so this is your solvent. Is this protic or aprotic? Protic, because you have a bond with an electronegative atom, oxygen. So that is not the best. Let's see if we can find some more. Is this a good nucleophile or bad nucleophile? Good. Is this solvent protic or aprotic? Because DMSO looks like that. Do you have an H attached with an electronegative atom? No. Yes. Inversion would be on this center, right? That center is not chiral. Therefore, even though there is inversion, you're not able to see it because this hydrogen is inverted, right? Do you get what I'm trying to say? If it's chiral, then you'll be able to spot the inversion, right? Since this carbon is not chiral, you're not able to spot the inversion. Inversion did happen, but it's not chiral. So, what's the last process? Is this a good base, good nucleophile? That will give you what? First order, 1. Okay, now question number 5. How many products do you get from this reaction? Let's see. This condition is what? SN1, SN2, first order? First order. First order means both SN1 and E1 happen, right? Yes. Good. And you're forming a tertiary carbocation, so there's no need for rearrangement. That's your what product? Substitution elimination? Because that's a first order reaction, so you'll form this carbocation, which can go to this substitution product. You do an elimination, you can have this as well as this. Which is better, A or B? Why? More substituted, right? A is the best, B not so much, but I can still list this as one of my products. If you have 3 boxes, if you have 2 boxes, just list A and that.
How come for the first order reaction side it was like 4 products?
In that case, we had something else. Because having a bond on this side is different. It's the same as having a bond on this side. If these 2 ends were different, then you'll have 4 products. All right? Now you have 3 products. if it attached on the other side of the carbocation, this center is not chiral. Therefore,
So is the answer 2 or 3?
answer is 3 ideally. If you have 2 boxes, put that and that.
Okay.
All right. So you want to stop here? Since I wish I could, but unfortunately not. No. So it's a great semester. It's an awesome semester.